Hi everyone, in this presentation I want to talk about our paper Tabbed Out, Subverting the Android Custom Tab Security Model. In this paper we uncovered 6 new vulnerabilities on the Android Custom Tab component. I'm Philipp and this is a joint work with Marcos Quarcina, Lorenzo Veronese and Martina Lindorfer. A quick overview of the presentation. First I want to talk about some background knowledge and introduce you to the concept of in-app browser and custom tabs. Then I will talk about our methodology that we used. After that, I will present 3 attacks that we identified in the paper. And to conclude this presentation, I will talk about some mitigation strategies. Okay, let's get started with some background. So Android supports what is called in-app browser. And an in-app browser is basically a component that app developers can embed in their applications and can then use to display web content in. A very common type of such a component is the Android WebView component, which is here framed in blue. Security-wise, the Android WebView component doesn't do a very good job in isolation. Applications can, for example, inject JavaScript code into the website, and websites can call native functions that are defined in the application and that are exposed to the web content. Each application that uses an Android WebView also has its own separate cookie jar. That means that another application that opens the same WebView doesn't have access to the same cookies as another application. This poor isolation between the web content and the application also opens doors for abuse. So a malicious application, for example, can inject malicious JavaScript code into the website to take full control of the website. In the other direction, a malicious website can call privacy-sensitive or security-sensitive functions that are defined in the application. So Android WebView is not always a really safe choice to use. Custom Tab is a more secure alternative to WebViews, and for example, Google especially recommends the usage of this component when an application wants to show third-party websites. So that means websites that are not directly associated with an application. A custom tab is actually an activity, that means a screen of the user's browser, so basically of the underlying browser. And out of the major browsers on Android, currently, Chrome, Firefox, Brave, and Edge support custom tabs. Now, because the custom tab is actually independent of the browser itself, the Open Web Advocacy, for example, suggests that custom tab is potentially an ideal solution for in-app browsers. A custom tab can, for example, be opened by a user click. So when the user clicks on this Open Wikipedia button, the Wikipedia website is launched in the underlying browser. And since it is launched in the underlying browser that also runs in a separate process than the application itself, there is a clear isolation. Nevertheless, custom tabs report some events, or also called callbacks, back to the application that launched it. And I will talk a bit about what those callbacks are later in this presentation. But note that Firefox does not support these callbacks. Now, the interesting thing about custom tabs now are that they share state with the underlying browser. So that means that if, for example, an application opens a custom tab provided by Chrome, then this custom tab shares its state. That means shares its cookies, for example, with Chrome. And this can also be, for example, used in single sign-on flows. And for example, the RFC on OAuth 2.0 in native applications recommends the usage of custom tabs for this purpose. Now, as a last thing, custom tabs also support a feature that is called bottom bar. And a bottom bar is this fully customizable part of a custom tab that is at the bottom of the custom tab. An application can also declare that an intent should be sent whenever the user clicks on this bottom bar. So an intent is Android's way of telling another application to perform a specific task. And in this example here, this intent is directed at the application that launched the custom tab. Okay, so our methodology to analyze the security of custom tabs is built on 4 pillars. So first, we reviewed the official documentation of custom tabs. And we did this basically to find general design flaws in the custom tab component. We then also reviewed the source code of Chrome, and we did this for 2 reasons. So first of all, this allowed us to identify functionality that is present in a custom tab, but is not documented. And second, it also allowed us to identify differences in the actual behavior or the actual implementation and the documentation. We also did some manual API testing. So that means we manually called the custom tab APIs with varying parameters to basically test edge cases and also verify our assumptions on the implementations. And then we cross-checked the actual behavior of the custom tab with the web standards. And this basically allowed us to identify gray areas in the web standards and also potential violations against web standards. Whenever we found a candidate for a vulnerability, we created proof of concept applications and also did some additional testing to measure its impact and also its capabilities. And when we validated the vulnerability, we reported the vulnerability to the affected browser vendors. And this led to 6 vulnerability reports and 3 CVEs. Okay, so let's talk about the attacks. So for all of the attacks, we assume the same threat model. We assume either a potentially unwanted application or an application that embeds a potentially unwanted library or an SDK. We then also assume that this application is in active use by the user. This application then opens a benign website or a target website in a custom tab. So based on this threat model and based on the methodology that I just presented, we identified 6 attacks on the custom tab component. 3 of those attacks are part of a new class of attacks that we call cross-context leaks. So I will first give a general overview of what a cross-context leak is, and then I will talk about 2 cross-context leak attacks, the state inference attack and the bottom bar URL leak. We also identified 3 attacks that are not related to cross-context leaks, and I will talk about one of them, in specific the bottom bar phishing attack. So a cross-context leak is very similar to a cross-site leak, and in case you're not familiar with a cross-site leak, a cross-site leak basically allows to leak content across sites in the web. And in a cross-context leak, we don't leak content across sites, but we leak content across contexts. So the goal of a potentially unwanted application is to leak information from the website. That means from the web context to the application context. And the first attack that I want to talk about is the cross-context state inference attacks. So remember that I told you that custom tabs report some events, or also called callbacks, back to the application that launched the custom tab. These events include events that are fired when a website has started loading in a custom tab, when it has finished loading in a custom tab, when the loading failed, or when the loading was aborted. And the interesting thing about these callbacks now is that these callbacks depend on the behavior of a website. And the behavior of a website can depend on the user's state of a website. So for example, a website may behave differently when the user is logged in compared to when the user is not logged in. And an application can now use these callbacks to infer such information about a user on a website. And our cross-context state inference attack is able to detect 4 such metrics. So, for example, redirections, status codes, content types, and timing. And all of these 4 can depend on the user's state on a website. So first of all, whenever a JavaScript-based or a meta-based redirection takes place in a custom tab, additional navigation started and additional navigation finished events are fired, one for each redirection. Also, when we receive a status code in the 400 and in the 500 range, and the response has an empty response body, then the navigation failed event is fired. Also, specific content types lead to the navigation failed event. So for example, when a video, an audio, or also a PDF is loaded, then the navigation aborted event is fired. And last but not least, we can use a timing-based approach. So that means we can measure the time between the navigation started and the navigation finished event, and then compare this to a baseline value. And depending on this comparison, we can infer some information of the user. So to make this attack stealthy, we can use the following approach. We have our potentially unwanted application, and this potentially unwanted application then launches a target website in a custom tab. The application then listens to the tab shown event, and as soon as this tab shown event is fired, the application launches another activity that overlays and hides this activity. And even though the custom tab is now in the background, the callbacks are still reported to the underlying activity. And an application can use this, for example, when the user navigates in an app. So when the user navigates from one screen to another screen, the application doesn't immediately open the target activity, but opens a custom tab in between. So here you can see a screen capture of this technique. So the user clicks on an item, a custom tab is opened, and this custom tab is immediately hidden by this other activity again. And as you can see, there is no clear visual indication that an attack has taken place. And an application can even do this without an activity transition. So an application can, for example, open the same activity that is currently being displayed and overlay the custom tab with this activity. The only downside of this technique is that the UI is unresponsive during the custom tab launch. The next attack that I want to talk about is an attack that we call bottom bar URL leak. I already told you about this fully customizable part of a custom tab, and also this intent that is sent whenever the user clicks on the bottom bar. The interesting thing about this bottom bar is that it contains the URL of the website that is currently opened in a custom tab. And this fact can be abused for a cross-context leak, since a URL can contain user-dependent information that can be used to de-anonymize a user. So many websites use some kind of automatic redirection to a URL that in some way or another contain user information. For an app to get this URL, all the application needs to do is lure the user into clicking this bottom bar. And how can an application do this? Well, an application can show context-related information in this bottom bar. So here you can see my Facebook page, and Facebook automatically redirects to this page when I visit facebook.com. An application can now masquerade the bottom bar as a cookie banner to lure the user into clicking either accept or deny. If the user clicks either accept or deny in the cookie banner, the intent is triggered and therefore also the URL is leaked. We can combine this hiding technique with a bug that we found in the implementation of the bottom bar in Chromium-based browsers. So the bottom bar has a fixed height, and we found out that an application can pass an element to this bottom bar that is larger than this bottom bar itself. And this element then overlays the custom tab and overflows the custom tab and therefore hides the web content. By adjusting the top bar color on Edge, we can also hide the URL of the website that is currently opened in the custom tab. And as you can see here in this figure, there is no way for a user to know on which website they currently are. On Chrome custom tabs and Brave custom tabs, we cannot hide the domain, but we can still overflow the bottom bar and hide the web content. And we can use this in a legitimate custom tab flow. So here we have an application that shows us a recipe, and we want to get more information about a recipe, so we click this more information button here. When this more information button is clicked, the website shows or opens the recipe's website in a custom tab. An application can now do the following. Instead of immediately opening the recipe's website, the application can launch a target website in a custom tab, for example, facebook.com, and then use this masquerading technique and the hiding technique. The user is now presented with a cookie banner and is prompted to either accept or deny the cookies. Because the user is privacy aware, the user will deny the cookies. This, however, triggers the intent, which also contains the URL of the currently opened website. The application receives this URL and therefore can de-anonymize the user. When the application receives this URL, the application opens the real website of the recipe and therefore hides the attack. The last attack that I want to talk about is the bottom bar phishing attack. So the bottom bar phishing attack is not a cross-context leak related attack, but it is, as the name already suggests, a phishing attack. So imagine that we have an application that contains a link to a post on Instagram. When the user clicks this link, basically the user is redirected to this Instagram post in a custom tab. And now there are many characteristics that basically convince the user that this is the real website of Instagram. So first of all, there is the domain name of Instagram visible in the custom tab. And furthermore, the profile picture of the user is also visible. And if the user was to navigate on the page, the user would see their messages, their posts, and so on. What a potentially unwanted application can now do is, it can now use this bottom bar for phishing purposes. So it could, for example, show a message that indicates some suspicious behavior on the user's Instagram page and basically prompts the user to change the password. This looks like a legitimate message from Instagram, but this bottom bar is actually controlled by the potentially unwanted application. When the user now clicks on this change password button, the user is redirected to a phishing page, which is then used to, for example, phish for the user's credentials. And this illusion works because of two reasons. So first of all, there is no visible distinction between the website and the bottom bar. So it's not clear where the website starts and where the bottom bar starts. And second, this shared state that we have between a custom tab and the underlying browser contributes to this illusion. So the user sees their profile picture, the user sees their post and their messages, and this creates some false sense of security on the website that a potentially unwanted application can abuse. Okay, so lastly, I want to talk about some mitigations. Cross-context leaks are very similar to cross-site leaks, as I've already mentioned. Custom tab-based attacks have some unique characteristics that allow to bypass a lot of existing cross-site leak mitigations. So for example, we have to understand that a custom tab navigation represents a top-level navigation. So that means that framing protection, such as for example used by the Xframe options header or the content security policy frame ancestors directive, are of no use. Also until very recently, same-site strict cookies were sent on navigations in the custom tab. Fortunately, this is not the case anymore due to a bug report that we issued and also another bug report of an unrelated third party that reported a bug with the same root cause. Nevertheless, same-site Lex cookies are still sent on all major browsers, but I will not go into detail since this is a separate attack. Last but not least, custom tab-based attacks until very recently could also bypass fetch metadata headers, or basically the fetch metadata headers between a custom tab and the underlying browser were almost not distinguishable. So that means that resource isolation policies and navigation isolation policies that relied on such fetch metadata headers could be easily bypassed. This is fortunately also not the case anymore, since this was fixed in the same fix as the same-site strict cookie issue. Okay, so what are some possible mitigations? First of all, we can extend the fetch metadata headers. So currently there is no way for a server to know whether a request originated within a custom tab. And we could inform the server about this by adding a new WebView directive to the sec-fetch-test header. The server could then decide if it should allow the website to be loaded in a custom tab or not. So for security or for privacy-sensitive websites, the server could opt out of being loaded in a custom tab. And the server could do this by answering with a redirection and setting an intent as the redirection location. This intent is then handled by the user's default browser, which opens this website. And this redirection strategy already works on Chrome. Secondly, we could also restrict state sharing. So we could change the model of custom tabs to, by default, not share state with the underlying browser, and only allow state sharing if the user grants permission to do so. So the application could ask the user for its permission. And this could, for example, be used in single sign-on flows. Google fixed some of the vulnerabilities that I presented, but unfortunately, Google did not carry out systematic mitigations, but rather implementation fixes. Also, Google will not fix the state inference attack and the bottom bar phishing attack, since they are working as intended. If you want to know any more information, then feel free to have a look at the paper and also feel free to drop us a message. Thank you.